Research Institute in Belgium. It has already been explained, MTBE is a fuel oxygenate, is frequently present in the environment, and it's mainly a problem because not of the toxicity, but because of its low odor and taste limit. So when it's in the water, you really taste it quite rapidly, and this can be a problem for drinking water winning areas. Legislations do exist in countries, so then remediation is obliged. Currently, for MTBE and also TBA remediation, classical methods are being used for oil or for fuel contaminations. And in Belgium, for the small gasoline stations, these are pump and treats with air stripping and sorption of activated carbon. However, for these pollutants, these techniques are not working well, and this is explicable by the high water solubility, which makes that air stripping is more difficult, and also the low sorption tendency, so sorption of activated carbon is not that good. Although these compounds are quite recalcitrant, bacteria do exist who can degrade MTBE via TBA to CO2. It's an aerobic process, and this will be the subject of this presentation. Okay, so why do we focus on bioaugmentation? So this means the use of microorganisms for remediation, let's say. And this is because an earlier study pointed out that only at 5 of the 8 tested sites biodegradation potential was present. And the second reason is that at Vito we enriched this consortium, which has been shown to be stable, a stable catabolic activity for MTBE and TBA, but also has some potential for biodegradation. Here you see, for instance, an example where we have a microcosm with the soil, which for nearly 500 days, where no removal of MTBE was observed. Once we inoculate it in the condition here represented in the green, you see the degradation. Each respike of the MTBE is degraded, and we're talking here about 15 milligrams per liter. So these were some indications that there is some potential. Here you see some more detail, where you see the degradation of MTBE, temporary accumulation of TBA, degradation, and it's associated with cell growth. For bioaugmentation, we can do it in 2 ways: pump the water and make an above-ground pump and treat system, or make the bacteria or inject them in situ, where you have to create good conditions. So we focus on the pump and treat system. This is our bioreactor. It's an upflow bioreactor, which has been presented already. So there is an influent, a recirculation, and an effluent. And the recirculation is to supply oxygen and to make it a quite homogeneous system. It has been shown in the previous talk that the system works. So the aim of the study that I would like to present is to prove, actually, or to test that the system can be implemented as a valuable alternative for the pump and treat system with air stripping and activated carbon. So what is needed? It's not only needed that you have some graphs that show that the technology can work under certain conditions, but we have to prove that it's robust and reliable, that it can work under different conditions and continuously. Upscaling should be possible, and also competitiveness with, for instance, this technology, so cost and efficiency also play a role. How did we approach this? So first we looked at all our available data and extracted some conclusions from that, and then we performed within the Minotaurus project some additional tests specifically dedicated to this robustness. So the first thing that we did some years ago is that we tested our culture here in suspension under different conditions. So we tested ranges for different parameters. And from there we reduced working conditions, which are listed here. So within these ranges, the culture really functions well. And when we compare these ranges, then we came to the conclusion that these are compatible with in situ and on-site remediation of the groundwater with attention for oxygen. Oxygen is needed, but we can deal with quite high concentration of the pollutants, and the pH and the temperature, they are within the range. Also co-pollutants, ETEX compounds are often present, so the system can deal with that. So MTBA is removed in combination with MTBA when oxygen is not limiting. In the remaining part, I will focus on 2 pilot tests. This is a picture of our pilot bioreactor. Actually, the system consists of 2 parts. The first part is the iron removing unit. It's not the focus of our research, but it's something that is necessary to make the second part workable. And this is the inoculated bioreactor. It's for 300 liters. It's a system where nutrients and oxygen can be added, pH and other parameters are controlled and are measured online. In our first, the first test, we did grow the culture in a larger volume, 60 liters. Then we inoculated it into the bioreactor, and at that time this was really an overkill of bacteria. But we wanted to be sure that the system worked. Once the system was shown to have activity, it was transported to a location, and there it was connected to a well. So this is real groundwater being pumped up. It contains MTBE 1 to 2 milligrams per liter, some TBA, some low concentrations of PTEX, and notice that oxygen in the groundwater is often limited. So the water goes first in the iron removal unit. When it leaves the unit, then the PTEX, they are already removed by the iron removal process, but MTBE and TBA, they remain. In the second unit, and this is another unit, there is a buffer tank in the bioreactor with recirculation, a buffer, and some post-treatment which is necessary to be able to play around with the system. So at all these different points, we have sampling points, and what I will show you at the next slide is the data from these ones, so what is in the in buffer, so what goes in the bioreactor and what comes out of the bioreactor, and some of these more downstream sampling points. So we sampled over time. In total, we followed the system nearly half a year. And the blue curve, this is the MTBE concentration that goes into the system in the bioreactor. The red curve is what goes out, and our regulatory limit in Belgium is 100 micrograms per liter. You see that in most cases it is below the 100 micrograms per liter, but you also notice here some peaks. And these are peaks that we can associate it with certain events that we did. For instance, when we shut down the oxygen supply, we received a peak, which proves that it's really biodegradation where oxygen plays a role. During the experiment, we also decreased, like in the column experiments from the previous talk, our hydraulic retention time, and each time when you reduce the hydraulic retention time, you can have a small peak, but quite rapidly the system is recovering from that. Also in winter, we stopped our system, just for safety reasons, for not being frozen in the tubings. And then after 1.5 months, we restarted the system, and you see that quite rapidly after the start, initially we have about 50% removal, we get a complete removal, and during that time, we try to make it a stable system, so not playing around with it too much. We decreased from 2 hours to 1 hour, and you see that the outcome or the effluent concentration is quite stable and below the regulatory limit. This is a similar graph, but then for TBA. So TBA, the blue curve, was sometimes present in groundwater, and when present, it was reduced in concentration. But importantly here is also there is no accumulation of the TBA from the MTBE. So recently we started new pilot tests, and we envisioned some tests, and the aim is really to evaluate robustness, so we want to do longer term tests. We want to subject the bioreactor to non-ideal conditions and situations which are real life situations. Test the reactor with different groundwaters and pollutants, mixed contaminants, different concentrations. Not only the performance, but also the costs and efforts needed to implement the technology, and for the maintenance and operational costs. They are important for us to evaluate the technology. Then more towards the scientific part, let's say, we developed in collaboration with Verbicom, another Minotaurus project partner, some monitoring tools where we can follow the inocular more in detail. Some data on the pilot test. So this time the system was placed at an industrial site. It was a storage place for petrochemicals, and when you see quite high concentration of MTBE and TBA were measured at the site, more than 60 and 100 milligrams per liter, and there was a really high dissolved iron concentration. What was the approach? So after characterizing the groundwater, we uploaded our system at Vito. Once it was uploaded and active, we again transported it to the site, and there the monitoring was performed and is still ongoing currently. This is at the Vito site, so there we have a well, and just before the water enters the bioreactor, we artificially have to pollute the groundwater. Here we use quite high concentrations because this was representative for the field. We work in a continuous mode, but when we do that, it's the lowest possible flow because we have to pollute otherwise too much of the groundwater, which we do not want. So this is the result of the first phase. So when we start the system, so we inoculated it, and initially it was not continuously just operated with recirculation, so no influent and effluent. So when you spike it, the concentration goes down. It took about 10 days. We wanted to speed up, so we added a little bit more, and at this time, more than 10 times less of inoculant was added in comparison with the first experiment. So after each spike, you see it goes down, and in the end of this phase, when you spike, you cannot even measure the concentration anymore because it's already degraded. Then at this point, after 40 days, we started continuous mode, so the dashed lines, they indicate what's theoretically added to the system, and the full lines is what was measured. So we also made here quite high concentration peak, but you see here the system removes it quite well. The site was not ready, so we have to, it's real life, to keep the system for some longer, so we did batch again with continuous addition of MTBE and TBA, but we could not measure it anymore. Then just before going to the site, we did continuous with some higher effluent concentrations, so 12 milligrams per liter of MTBE and 6 milligrams per liter of TBA, which is quite considerable, and you see that the system degraded quite well. Okay, so the system was ready to go to the field. And this is how it was transported to the field, and how it was installed at the field. Again, like in the first field test, you have here some concentrations. You see that the concentrations are lower than expected from the first sampling, because there we had 100 milligrams per liter of MTBE, but before pumping, the well was completely rinsed, and then it seems that the concentration were lower, but still quite significant. Okay, and then we have similar graphs as for the others, so we followed it in time. Here the first 3 months of operation are indicated, where here the green curve is the concentration of MTBE going into the system, and all the others, they are parts of in the bioreactor, effluent of the bioreactor, or the effluent buffer. And you see they are lower. Sometimes it's not completely degraded for the MTBE, and it fluctuates somehow. But I have to mention that during the first 2 months, we had really an unstable flow for all types of reasons, electrical shutdown, technical errors, and so on. But these provided us ideal test conditions for the non-ideal situations, where realistic situations where bioreactors in the field can be subjected to. But once it is more stable, you see that all what is present is removed. For TBA, the data are a little bit more excited, as there the concentrations are higher. This is the influent, and this is the effluent. I think it's clear that the system can remove TBA, which is a big advantage when compared to air stripping and activated carbon, which really cannot deal with TBA at all. Here you see the lower concentrations. So you see also here it's a little bit unstable when the flow is unstable, but the concentration in the effluent are really, really low. As mentioned, there were some non-ideal conditions, so during this unstable period, at several time points, the temperature in the system was above 30 degrees, which from our first system is what the bacteria do. And also, there were some extreme pH variations at the 30, which you can see here. So there are a number of parameters which are continuously locked. When you look at the red curve, so normally it's 7, you see here we had really, really, really big fluctuations from pH 3 to 10. So when you look then back to the results with these extremes, you see that after this event, our influent and effluent of the MTBE were really close together. So at that time we really thought, okay, we have to go back for a re-inoculation but we give it a little bit of time and you see